Hello, I'm Canchen, and in this lecture we'll be going over borrowing. So as an overview for what we'll cover this lecture, we'll review ownership, talked about in the last lecture. We'll introduce borrowing and dereferencing. We'll talk about some common errors with borrowing, and then we'll go over some practical examples. So as a review of ownership, remember that each value in Rust is owned by something, and there can only be one owner at a time. When we change the owner, it's called moving, and that when this variable goes out of scope, this value that it owns ends up being dropped. Recall that we can transfer ownership. So in this case, we let s1 be a string, and s1 owns this string slice hello. Then when we do this assignment, s2 equals s1. S1 is moved to s2. S1 no longer exists, and we transfer ownership of the data that S1 is pointing at to S2. So, however, now we consider the situation, what if we don't want to move this underlying data? Is there any way we can get around it? And the solution is to use borrowing. In this case, much like how you can have a pointer to something in C++, we can have a reference to a variable in Rust. So in this case, the way you would get the reference is by putting an ampersand at the start of the variable name, so ampersand s1, and we represent that. We can also do this for data types to show like what type something is. So here s is a reference to a string, and the way this code works is instead of handing calculate length s1 and giving this function ownership of this string, we give it a reference instead. And then here, s is a reference to a string. Then at the end of calculate length, s is dropped. So just the reference is dropped. And then we still have access to s1 in the main function. So this is the idea behind borrowing. And kind of to more formally explain it, remember that the ampersand represents the reference, and this lets us refer to a value without taking ownership of it. And this is also called borrowing. And then it's similar to references and pointers in C++, that you can refer to a value without needing to get a copy. However, some problems with C++ pointers and references is that suppose we have two pointers to the same object in different functions, and then one might modify the object without the other knowing, and this might cause some bad things, like some conflicts, right? Or another case where if we have an object but it gets dropped without the owner of the reference knowing. So like let's say I pass in a pointer, and then in the function I set it to null, and then when it comes back the pointer is garbage, right? Extra bad things can happen here. So the solution is Rust references come with training wheels to help prevent these bad situations. So we introduce some borrowing rules. At any given moment, you can either have one mutable reference or an infinite number of immutable references. And then a mutable reference must always refer to a mutable variable. And then references must always be valid. So you can only reference existing variables when they're in scope, and the compiler will check this. And then if you still want a null type anyways, you can use option potentially, right? And this will force you to check if it is null or not. So here, in this example, we declare x as a mutable string, and then y is a mutable reference to x. So here, when we try and use push string, which takes a mutable reference of x, we have an error because we can't have a second mutable reference to x. Y is already a mutable reference to x, so we can't have a second one, right? So this is one case of how borrowing works. Another case is shown here, where first we declare class to be a string, and then when we pass it to say hello borrow, we give hello borrow a reference to a string instead. So we pass in and class, and this gets assigned to name, which is a reference to a string. And then at the end of hello borrow, this reference is dropped, but the original string that it refers to, class, is still in scope. So we can later pass class to say hello. And then after say hello takes ownership of this string, it gets dropped at the end of this function. To access the value inside the reference, we can use a star, so to dereferences. And this works similarly to pointers in C++. And the usual use cases for dereferencing are if we have a mutable reference, we can dereference it to mutate the value. And this is the most common way you'll use mutable references. For immutable references, if you try to assign a value to that variable, it'll try and move into it, which is forbidden, or you will create a copy of it if it's defined using clone. And this can be slow, so you want to avoid this in most cases. So if you're trying to dereference on an immutable reference, you should reconsider what you're doing. So we'll walk through these code examples now. Here we have x as a mutable int, and then we'll take a mutable reference to it, and we'll pass it to the function add1. And then in order to actually change the value inside of num, we have to dereference it first. So the code is pretty self-explanatory. Here, when we have a class as a string, and then we try and assign it to new name, this doesn't work because we cannot move the value out of the reference. We can only take potentially another reference to it. So in this case, because it's a mutable reference, we can dereference it to change the value. Because this is an immutable reference, dereferencing it will try and move it out, and you should avoid it. Here we'll talk about when to dereference. Usually, you should dereference when you need to get a mutable reference to a primitive type, or if you're using a mutable iterator, like when you're iterating over a vector, you can dereference to change the elements. And some cases when you don't need to dereference are if you're accessing vector elements using brackets, you don't need to dereference. And if you're calling functions on a mutable reference to something, you don't need to dereference it. So for example, if you have a mutable reference to a string, you can just call the functions. So here is a common situation, a common issue that people run into with references. And we see, well, here we only have one mutable reference and there's no ownership transfer, right? But what's the issue? And the issue is, if you recall, we can only have one mutable reference or an infinite number of immutable references, but we can't have both. So if we try and run this code, cargo will complain. We have an immutable borrow, but then we make a mutable borrow after this, and we try and use them both at the same time. And the reason why this isn't allowed is the immutable reference supposes that the data will stay the same, but then this mutable reference could potentially let you change that data before the immutable reference gets to be used. So there's a conflict here. And the way we can fix that is we can just use the immutable references before we get a new mutable reference so that these references can be dropped. Another case, common error, is when you try and return a reference. So here the error occurs because we declare a string s inside the function, then we try and return a reference to it. But at the end of the function, s goes out of scope. So this reference is essentially pointing to nothing. Here, the code won't compile because of the error mentioned above. And we can fix this potentially by using lifetimes, but that's outside of the scope of this lecture. Or in this case, a simple solution would be if we just wanted to return the information inside this string, we could just return the string directly instead of passing a reference. And we can just hand the ownership of s back over to the main function. We'll talk about how to iterate over vectors using mutable references. A mutable iterator. So instead of indexing each element directly by looping through the indices, you could call v.itermute to get a mutable iterator over v, and then each of these elements are of type mutable reference to an integer. And then remember, we have to dereference the mutable reference in order to be able to change it. And then these two pieces of code have the same functionality. It's just that one is using an iterator and dereferencing the mutable elements. And then the bracket notation, implies that you're getting a mutable reference already, so we don't need to dereference it. To sum up, like the difference between the different vector methods, if you just use indexing, you will take ownership or a copy of the value. If you use an ampersand, you'll immutably borrow the value, right? Because that's getting a reference to it. If you use and mute, ampersand mute, that is getting a mutable reference to it. And in this case, remember that in order to get a mutable reference to something, the initial variable must also be mutable. And then we introduced this get function before, which returns an option type. So in this case, it won't panic if it goes out of bounds. And this gives a reference to that object inside the vector. But you can also use get mute to get a mutable reference to that object. Right? And again, in order to get a mutable reference, the variable must be declared as mutable to begin with. That's all the content for this lecture. Homework 4 is released today, and it'll be due in a little over a week from now, next week, Friday. Thanks for listening.